This resource is the fourth in a 5-part series on vectors. Part 1 defines vectors. The component form for a position vector is presented with an example. We also discover how to find the magnitude of a vector. Part 2 considers basic operations with vectors. We look at adding and subtracting vectors in component form with examples. We also consider scalar multiplication of vectors. Part 3 considers writing the vector in terms of its magnitude and direction. Part 4 describes how to find the resultant force when two different forces act on the same object. Part 5 looks at the dot product of two vectors, looking at multiple examples, including a word problem. In the last resource, we considered forces and how to describe them as position vectors. In the real world, an object is rarely affected by only one force. There are usually multiple forces on an object at any given time. What we want to find is the resultant force, the overall effect of all the forces acting on an object. For example, for the plane on the cover slide to fly forward at a constant altitude, the thrust must be greater than the drag, and the lift must balance the force of gravity. Or the plane on this page, which wants to fly straight, but is blown off course by the wind. But how can we find this resultant force? First, we need to write all the individual forces as position vectors. Next, we add those position vectors together. This gives us the resultant force as a position vector. We then find the magnitude of the resultant force. To finish, we find the direction angle of the resultant force. To find the magnitude of the resultant force, we take the square root of the sum of the squares of the x direction and the y direction components. In other words, we square the values for a and b from the resultant position vector, add the results, and take the square root. To find the direction angle theta, take the inverse cosine of the ratio of the a value from the resultant position vector to the magnitude of that vector. Now that we have the basic process for finding a resultant vector, let's look at an example. Suppose two children, Al and Bonnie, are pulling a wagon. Al pulls with 30 pounds of force in a direction that is 10 degrees north of east. The older and stronger Bonnie pulls with 60 pounds of force in a direction that is 20 degrees north of west. We want to find the resultant force. How much force is imparted to moving the wagon? What direction will the wagon go? First, we need to find the position vector equivalents of the forces that Al and Bonnie impart on the wagon. For Al, the magnitude of the vector is 30, and the direction angle is 10 degrees. Remember, direction angles are measured from the positive x-axis, or due east. We plug those values into the formula to find the position vector. Doing the multiplication, we find the value for the position vector equivalent for Al's force. Now we shift our focus to Bonnie. She pulls with 60 pounds of force, so that is the magnitude. Because she is pulling in a direction north of west, we need to subtract the 20 degrees from 180 to find her direction angle theta. This theta is then equal to 160 degrees. We plug those values into the formula. This gives us the position vector for Bonnie's force. Note that the x direction component is negative, because Bonnie is pulling to the left. To find the resultant force, we add the position vectors for Al's and Bonnie's forces. We insert the values we just found for those position vectors. rearrange so we can combine the x direction and y direction components. Doing the addition, we get the position vector for the resultant force. Now we want to shift this back to the magnitude and direction of the resultant force. First, we need to find the magnitude of the force. Plug in the values for A and B that we just discovered. Using the appropriate order of operations, we find that the resultant force has a magnitude of 37.18 pounds. Now we will find the direction of the resulting force, using the formula we discussed earlier. Plug in the values for the x direction component and the magnitude. Solving, we find that the direction angle theta is 136.2 degrees. Theta measures the angle from due east. We usually describe angles in their lowest terms. We want to find an acute angle equivalent of this theta. Because of our value for theta, we will subtract theta from 180 degrees to find a better description of our angle of force. Doing so, we find that the direction the wagon moves is 43.8 degrees north of west. Putting all our information together, the wagon pulled by Al and Bonnie is acted on by a total force of magnitude 37.18 pounds of force in the direction of 43.8 degrees north of west.